Thank you very much. I know we're pretty far into the conference, so I appreciate you spending roughly the next 45 minutes with me, watching me present on some relay-related techniques, and also thank you so much to the ZeefCon organizers for having me. So today I'll be presenting something that I refer to as relay your heart away, or more specifically, an OPSEC-Conscious approach to taking over port 445. A little bit about me. My name is Nick Powers. I've been working on the adversary simulation team at SpecterOps for a little over 3.5 years now. I started as a consultant, then senior consultant, and currently working as a service architect, where mainly contributing and supporting our adversary simulation team with things like this technique, hopefully, that we get to make use of on assessments. Most of my career has been focused primarily on something like offensive security related, so pen tests, red teams, more so red teams at SpecterOps, and some of my personal work-related interests include initial access techniques, some Windows internals, as well as things relevant to targeted authentication relay attacks. And my handle on Twitter, Bloodhound, Slack, and most other social media is Zenergy. So, a very brief agenda of what we will be covering. We'll start off with why does this matter? Why do we even want control over port 445 in the first place? What problem are we trying to solve? We'll go over some existing solutions to this problem. It's not new. It's something I think red teamers and pen testers have struggled with for years, and there's already solutions. This is just another approach to that. We'll go through debugging some of the relevant drivers to this technique to hopefully better understand why this works under the hood. Then we'll go over some tools to automate, as well as a demonstration of why this has been impactful for us, for example, on assessments. And before we get into the material, 45 minutes, unfortunately, is not enough to cover all of the relevant things to this technique. So all of the SOX proxying and reverse port forwards, tunneling tradecraft in general as it pertains to operating out of a C2. So I'll reference some of that, but it is kind of assumed knowledge. Again, if you have any questions or how some of that works for us on assessments, more than happy to chat about it after the talk. Some entry-level knowledge will probably be helpful regarding relevant or popular NTLM relay techniques currently, as well as coercion and the protections associated. None of this is required. It'll just help make sense of some of the demo stuff at the end. And then lastly, an entry-level knowledge of reverse engineering. I emphasize the entry because I'm not an exceptional reverse engineer, so even if you do know reverse engineering, hopefully this will make a decent amount of sense when we step through that. And also, before we dig into some of the specifics, to kind of elaborate on why we would be interested in this in the first place, the problem that hopefully this will solve for some people is that currently, as it stands, conducting SMB-based NTLM relays over C2 specifically, which is what's relevant for us on assessments, for example, is kind of a difficult thing to do. There are existing solutions to the problem, but none of them are incredibly straightforward. All of them come, like most other things, come with associated operational security risks. The solution that will hopefully come from this is a way to take control of the port that we're interested in for SMB-related NTLM relay attacks, but with hopefully some of the OPSEC concerns kind of eliminated. So, relevance of taking control of this port. I'll admit that my experience is biased towards how we conduct our red teams. So I lean towards, or what we've leaned towards heavily for the last 2-3+ years is targeted NTLM relay attacks, the popular coercion with things like Petit Patam, Lee's printer bug related coercion technique. And the reason we focus on that a lot is because even in incredibly mature organizations that, or what I would consider mature, that we target on a regular basis for our customer base, these are still attack avenues that work very, very consistently because there's a lot of stuff to remediate to make sure everything is locked down properly. So when I say it works regularly, what I'm typically referring to, the most popular for us, would probably be HTTP to LDAP related relays. So take advantage of object takeover primitives that our colleague Elad has published some research on, like shadow credentials, resource-based constrained delegation. We also have SMB or HTTP to HTTP relays, so that's like escalation 8 or SCCM takeover 4.2. That's the takeover primitive where you relay to the SCCM admin service API, if I remember correctly. Then there's SMB to HTTP targeting SMB, so this is a lot of the SCCM, the recent SCCM takeover primitives, as well as a lot of other general relay opportunity. And then the demo that we'll be going over at the end will be SMB or HTTP to MSSQL, more specifically the SCCM takeover 1 primitive. That'll be the demo. But the reason we're going over all this is because depending on your perspective of access in the target network, taking over or controlling the inbound SMB traffic, like what you have potentially coerced or maybe even poisoned in some capacity, can be more involved depending on your perspective in the network. So what I mean by your perspective in the network is if you're operating from a kind of traditional like pen test scenario, like you have a Linux box plugged into the network, you have a VM deployed in your target environment, then this could be as simple as just like your root, you bind to 445, you can conduct like your responder or poisoning-based attack, and it can be relatively straightforward. It can also be kind of straightforward from a Windows machine, depending on your perspective, by doing something just as simple as disabling the LAN server service. You reboot the host, 445 is no longer bound. You can do like your reverse port forward functionality from there. Opening from it or operating from a compromised Windows host, however, so like operating through an agent, for example, this is typically a lot more involved, and ultimately we want to end up with some sort of reverse port forward functionality. So what I mean when I say that is like you coerce some traffic, it comes back to your compromised host, and you need a way to tunnel that traffic out to do like some type of relay, tunnel it back into the network. And the root of the problem is that by default, the Windows kernel is bound to 445 TCP on all network interfaces for both IPv4 and IPv6. And you can see a little like pseudo terminal here where we do like a netstack command and show that 445 is bound listening by something. So before we dig into this specific approach, I wanted to reference existing solutions that I think are relatively popularly abused currently for solving this problem. And the first, and the one that I see referenced probably the most currently, is techniques relevant to leveraging the WinDivert driver for interacting or redirecting inbound traffic. So when you abuse the WinDivert driver, you load that signed driver. It's most likely EV code signed, so you can load this open source driver. And WinDivert specifically is defined as a user mode packet interception library. And there's a lot of really popular projects that make use of the WinDivert driver, like Portbender, that's written as a reflective DLL. There's Sharp Relay, that's C# that interacts with the WinDivert driver. StreamDivert, Divert TCP, C++, as well as this, the HWFW bypass project, which is over 10 years old now, I think. So leveraging WinDivert is not a new technique, but it's something that is still very popularly abused, and lots of projects implement this. There's also CCOB, or Ethical Chaos's LSA authentication provider, or the LSA Relay X project, which is a really interesting approach that hooks the NTLM and negotiate authentication packages and redirects those authentication requests, in his case using named pipes. And then lastly, like I already mentioned kind of briefly, is you also have the option to just reconfigure the LAN server service to a disabled start type, and then when you reboot the box, 445 will no longer be bound. You can do your reverse port forwarding, and everything will work. But some of the existing OPSEC concerns or struggles that we have with that during assessments is, in the case of loading drivers, or WinDivert specifically, or other drivers that would accomplish this for us, there's the, like mentioned in the last talk, there's plenty of potential for like if you interact with the driver in such a way that like error handling is not accounted for appropriately, it's very easy to cause blue screen of death. And this isn't super viable, at least for us, especially if we're operating on like critical infrastructure, or even just on a normal workstation where we don't want to interrupt like day-to-day operation. Also, leveraging a driver could be a single point of failure regarding detection, so you're relatively limited in terms of the options you have for loading drivers, and when something like WinDivert is so commonly abused, even though it is a legitimate driver, it's a pretty high fidelity thing to look for in an environment. If you're not using that for software in your environment, it could be a relatively clear indicator of compromise. And then lastly, still related to loading drivers for this would be you also need some way to interface with that driver. So like the ioctals potentially exposed by WinDivert, you're going to need to like reflectively load a DLL to interact with those, or leverage like some type of .NET dynamic execution, unmanaged PE, like some kind of PIC shellcode or a BOF. You'll need something in addition to the driver that also has its own set of operational security concerns. As it pertains to using custom LSA authentication providers, this is a limitation of how Windows and LSA custom providers for authentication providers for LSA work, but you can't unload those custom providers until a reboot. Like the reboot will be what unloads that custom provider. So having like a custom DLL that's doing something malicious hanging out in memory of LSAS, and the only way to get rid of that being a reboot is a concern for us operationally, as well as you also have general stability that could be an issue. And if there is a problem with the code that you've written, or you use it in an unexpected way, an error is not accounted for, LSAS could reboot, and that would cause a forced reboot of the host operating system. And I also mentioned you can set the landman server service to a disabled state, but oftentimes we just can't reboot a host. We just can't reboot a host in the middle of an assessment for a number of reasons, so sometimes that's not an option for us as well. So this had been a topic that was on my list for like hopefully finding an alternative solution to for probably like over 4 years, and eventually just sitting down one day like 4 or 5 months ago, more or less accidentally stumbled on a solution. And it started with looking at drivers associated with 445 being bound in the first place. So like I mentioned before, I'm far from being a professional reverse engineer, but the tools that I started with to start going down this rabbit hole was primarily System Informer, the free version of IDA, WinDebug, just to do basic static dynamic analysis. And to kind of redefine what our goal here is, we want to do, something that releases the target port without requiring a reboot, without loading a driver, ideally, or without loading an arbitrary module into LSAS. So where can we start? Well, we already know that we can set the landman server service to disabled and reboot the host, and we will end up with 445 not bound, so we can do something in terms of analysis from that point. And by simply resetting the start type of the landman server service, so we disable landman server, we reboot the host, 445 is not bound. But we know that we can set landman server service back to an auto start type, and it re-enables, and all of the associated resources with 445 being bound also come back into play. 445 is bound again. So this provides us a starting opportunity in terms of both dynamic and static analysis, because we can get 445 unbound, even though it's after a reboot, and we can re-enable landman server service, and 445 will rebind, so we can start to like inspect what's happening under the hood there. So what do we want to do? We probably want to start by identifying the process, or like the resource on the host that's actually binding to this port. We want to triage relevant loaded modules, or in this case, some drivers. We want to narrow down the drivers associated with this behavior that we want to learn more about. And this last note is just because I wasted like at least a week statically reversing the wrong versions of DLLs. So definitely make sure, because you're going to be doing kernel debugging if you're looking at this, you use something like WinBindex. So you're using, if you have like the machine that you're doing the reversing on versus where you're actually doing the debugging. If you have different versions of the DLLs, it's going to cause problems when you're doing like static analysis, for example. So WinBindex is a great resource for that. So to kind of get us started, we can run a simple PowerShell command here. We see that it is PID of, or it's the system process specifically, a representative of a lot of kernel-related activity that's bound to port 445. And I use, this was either Process Hacker or System Informer here on the left to look at the modules. We see a bunch of drivers and their descriptions. So I did what potentially some other people in the room would do, and I just copied all that into ChatGPT. I said, hey, what's relevant to like SMB and NetBIOS? So that gave me, that at least narrowed down the list from like 30 plus drivers to, you know, like 5, 6, a more like digestible amount of drivers to start looking at. So used IDA free then in combination with symbols for a lot of these drivers to just start looking at interesting functions that seemed like they were related to like binding ports or related to SMB communication or NetBIOS, just things that seemed like it might have something to do with what we're interested in. And I came up with a very, very long list of functions, and even though we narrowed down a little bit, it was still, this list was at least like 50 or 60 functions, but some of them kind of stood above the others, like iNet Acquire and the TCP IP driver was interesting. A lot of interesting functions to start looking at in terms of static analysis. So we configure a kernel debugging. This was actually the first time I had ever configured kernel debugging. It was less arduous than I expected, but configure that on a remote host, snapshot the host when 445 is unbound. So like I mentioned before, you disable LAN server service, reboot the host, it's unbound. I snapshot it because I'm going, or hopefully to start doing dynamic analysis, we will be re-enabling the service regularly to get a better understanding of what's happening. So we do that, just write this PowerShell one-liner and like hotkey it so I can like revert the snapshot, re-enable LAN server service, revert the snapshot, re-enable it, and start setting breakpoints. So we set the breakpoints for the functions, some of the functions mentioned in the last slide, and eventually that led to inspection of this function called iNet Acquire port in the TCP IP driver, which was reliably hit after re-enabling the LAN server service and doing the reboot, and regularly hitting this function that seemed like it would be very relevant to start getting a better understanding of what's going on here. But even though I was hitting that breakpoint, I wanted to make sure that hitting that breakpoint was associated with the rebinding of 445. I wanted to definitively know that, and thankfully that's a relatively easy thing to do with deep kernel debugging. So I tried to keep as little code, especially pseudocode from IDA in these slides. I know nobody wants to just look at like decompiled code that looks like nonsense, or maybe that's just me, but just 2 tiny snippets. This one's from that iNet Acquire port function that I mentioned in the TCP IP driver. The reason this stood out was because one, there's a subsequent call to the is port in exclusion, and I guess before I start describing the specifics, the reason this was interesting is because just the name of the port is like, I wanted to know definitively that this has to do with 445 rebinding. And the name of the function, as well as subsequent function calls like is port in exclusion list, it seems like this is associated with that behavior. So because the iNet Acquire port function makes a subsequent call to this is port in exclusion list, and one of the parameters for that is port in exclusion is a data type, more specifically an int16, that could very likely represent a port number, or a TCP port number. That was interesting, a good starting place for dynamic analysis. So I stepped through a couple of these breakpoints. It's triggered when I re-enable LAN server service. I step through until I reach a couple calls to this is port in exclusion list. And because of the fast call calling convention, we know the function has 2 parameters, this v68, that's the thing we think is likely a port number because it's int16. And if we step through, fast call calling convention tells us that based on the function's prototype, that variable will end up in the RDX register. And if we asked WinDebug, it returns. Now we know definitively that when I rebind, when I re-enable the LAN server service, eventually this function is towards the end of that call stack and associated with that rebinding behavior. We see 445 specifically in the RDX register. Okay, but all of this is associated with binding 445. That's not really what we're trying to accomplish here. But how can this call stack, like when we hit iNet port acquire, help us understand the unbinding process? So initially I thought like I'm gonna have to dig through maybe like ioctals exposed by some of these drivers relevant to the binding process, and maybe there's something exposed that would allow us to reach a code path that we could unbind with. Thankfully, I didn't have to dig that deep. Starting from the servnet.sys driver within the previous call stack mentioned, so we see that here towards the bottom, some calls from servnet. The symbols started to very easily allow for identification of like what was happening when we were binding compared to what would likely be happening when we were unbinding. So you see like when we just identified the relevant call stack for the binding process, we saw servnet workstation open listen socket. Well, if you just look at the symbols, there's a close listen socket, or allocate endpoint, there's a close endpoint. And it was pretty easy to correlate what would likely be the functions responsible for unbinding. And I start looking through cross references. So like if we reference the call stack for, this is what we definitively determined was associated with the binding process. So if we start down here towards some of the functions from servnet, we can just dig through some of the cross references, see where these functions are used within the driver, and eventually, before we have to take too many steps, we go from the net close endpoint to this crazy long function I'm not going to make everybody listen to me say, and we eventually reach driver unload, which some people in the audience probably have an idea of where I'm going with this, but this was definitely interesting. So how can we determine if unloading this driver or functionality associated with this driver unload function could be, or we could reach that in some way? Well, our first option would be we can just be a good reverse engineer, step through all of the disassembly until we have a relatively good understanding of what's going on in the driver. Or you can just let Jesus take the wheel and start disabling services. And I'll let everybody assume which approach that I took. So why are we stopping services in the first place? Well, if we stop a service, or more specifically a service like a driver relevant service, this should ideally call its respective driver unload function. I say should because not all drivers are like implement this correctly, but it is a prereq of like the WDM framework and some other like guidelines for development of drivers. And so if we just try to stop servnet, we see this error, unable to stop service, something about dependencies. So why are service dependencies relevant? Well, MSDN defines a dependency as something that specifies the name of services or groups that must start before this service starts. So in most default builds of Windows, the servnet service is a dependent of the serve2 service, which is then a dependent of landman server service. So there's like some nested dependencies here. And this is even more encouraging because if you remember, we've mentioned 3 or 4 times now, you can stop the landman server service, reboot the host. Now we've worked through the static and dynamic analysis and we're like connecting the dots back to the landman server service through these service dependencies. And you can kind of see here, if you're using like Process Hacker, System Informer, you can very easily list service dependents as well as just where that information also exists in registry here. So we've done static analysis, we've done dynamic analysis. Somehow like service dependencies are relevant to all this stuff, but how do we like connect all of this information and hopefully turn understanding the binding process into successfully unbinding port 445? Well, we can reconfigure these services that we've better understood through this analysis in a specific order because of the dependencies. So like we've mentioned several times now, we changed the start type of the landman server service from auto start to disabled. The reason we do this is because landman server has, there's this concept of service triggers, things that will potentially automatically enable that service. There are service triggers associated with landman server service that will constantly hit the service. So you need to configure it to a disabled state because if you just stop the service trigger will be hit in like less than 30 seconds. It will re-enable. So you need to reconfigure the start type. You do that, then you stop the service, then you start the serve2 service because that's the next dependency that we've identified. then you stop the serve net service, and then the fifth step is you just pray that 445 is unbound, hopefully. But instead of praying, we're actually going to try to be decent reverse engineers here and step through a little bit more debugging to actually make sure that our assumptions are validated here. So we talked about the inet acquire port function for the binding process. Well, symbols tell us we can potentially assume that inet release port is the unbinding equivalent in TCP/IP. And similarly, we also see another call to is port in exclusion, which has that same int64. It's probably a port. We can set some breakpoints and validate. So we set those breakpoints, we step through, we hit them again consistently when we disable these services in a specific order. And then finally, we can validate that when is port in exclusion is hit and associated with the release port function, it is definitely associated with unbinding port 445 here, as we see in the RDX register. And then finally, we just validate with PowerShell or whatever your tool of choice is, and we see that 445 is successfully unbound. So to kind of make sense of all the static stuff we've looked at, dynamic analysis, if you want to start from the beginning, the reconfiguring services, imagine that's below the graph here. We stop the services. When we finally reach stopping the servnet service, that calls the driver unload function. That makes more function calls in the servnet driver, which eventually reaches this servnet workstation close listen socket function, which then makes more virtual function calls to the ADF driver, ultimately filtering up to this inet release port function that is responsible for unbinding port 445. So for anybody that's interacted with the service control manager regularly, you can probably assume this is a relatively easy task to pull off with existing tooling. But for those who don't want to make a series of 4 manual interactions with the service control manager, I did write a simple BOF as well as in packet-based Python script to automate some of this for you. But first, before we look at that, I ran into a couple things while I was testing, also things that we've run across during red team engagements that would be relevant to consider when you're abusing this technique. First of which would be, however you're interacting with the service control manager, it's important to be mindful of how you're interacting with it. And what I mean by that is a lot of tools, especially offensive security related tools, will default to leveraging name pipes for communication with things like the service control manager, or this npcacn_np representation of RPC communication. It's important to remember that when we're disabling these services, you're disabling the things that allow you to communicate over named pipes or SMB communication. So if you're targeting a remote host and you disable all of this stuff, then yes, 445 is unbound, but you're also unable to communicate over named pipes to re-enable it. So something to consider. You're not completely out of luck because you can also interact with the service control manager using RPC over TCP. And there's plenty of tools that allow you to do that. I'll give some examples here in a second. One big bonus, in my opinion, of leveraging this technique to disable 445 is that once you've disabled the service, you can just simply set the start type of landman server service to auto start, wait 30 seconds or so, or however long it takes, not very long. A service trigger will be hit for the service, which re-enables landman server service. And because serve2 is a dependent of landman server, that one gets re-enabled. And because servnet is a dependent of serve2, servnet gets re-enabled. So long story short, you just set landman server back to auto start, you wait for a few seconds, 445 is rebound, and hopefully not too much issue from that point forward. So again, wrote 2 quick implementations of automating this for post-exploitation. What that kind of looks like here, and I guess before I explain any of this, I just wanted to give a reference to WMI exec pro, which this was very largely based on because it defaults to RPC over TCP communication. So just kind of hacked together a version of that automates these specific service control manager interactions. So you can see in the output, landman server service, we set it disabled, we stopped some other services, and then the simple functions that I implemented were just stop, check, and start. So we stop, it does the things here, we check, it checks the status of all of those services. And the core of my logic here for making the assumption that 445 is unbound is just really checking servnet, because we can assume, due to the dependencies associated with these services, if this one's stopped, that the servnet driver is unloaded, therefore 445 is most likely unbound. So this is what the Python script looks like. In this example, I'm proxying it in like we would on most assessments. And if you, again, the benefit here is if you disable 445 on a remote host, you'll still be able to use this to like check and re-enable 445. Same thing with a BOF, basically. And again, another shout out. I definitely didn't reinvent the wheel here, leveraged existing Python and like BOF related code to conduct these service control manager interactions, but same function, stop, start, check, super simple, does the service control manager interactions, and will hopefully unbind and rebind 445 for you. And I like to make this note because these two specific, like the BOF and the Python script, I probably won't revisit, and the reason for that is like if you need to interact with services, there's an endless number of tools to do that. Use the SC binary, use Impacket, use like there's hundreds of tools available, and it's a simple series of interactions. So I'll definitely publish my proof of concept tools, but if there's a case where like there's different dependencies or anything like that, it hopefully should just be simple enough to use the existing WMyExec Pro project or the SC binary. I've seen a couple of our consultants leverage SC from a remote Windows machine that they just proxy in over like Proxifier or ProxyCap. And one note about using the SC binary from like a remote Windows host is that sc.exe defaults to RPC over TCP, so good option for like if you want something that can disable and also re-enable remotely. Same thing with WMyExec Pro, defaults to RPC over TCP. And you can, just like the logic of the BOF and Python script that I'll release, you can just simply check the status of the servnet service. That's like the root of kind of controlling what we're talking about here. And if it is stopped or started, you can generally make the assumption of whether or not you've successfully unbound or rebound the target port. So I wanted to give I guess before I give the demonstration, I want to give a shout out to both Garrett Foster as well as Chris Thompson and everybody else associated with the SCCM research, lots of people from the community, another one of our colleagues, Dwayne. These two specifically because I had not abused a lot of the SCCM related tradecraft up to this point, but I personally think that this is significantly more impactful because of their work, because of the additional relay primitives that they've discovered in the last couple of years. And Chris got me set up in an SCCM lab to demo some of this. And if he hadn't done that, I'm sure some people here know SCCM is difficult enough to set up. I don't know if I ever would have demoed this. So Chris was a huge help. Garrett walked me through making sure I had like a good understanding of the abuse primitives that were relevant and just using his like SCCM Hunter tool. Okay, so I guess before I start, I'll make a quick note of what we already have that we're kind of just making some assumptions here. We already have a compromised host in a regular domain user context. We've already opened up a SOCKS 5 proxy, or you can use SOCKS 4a. And another note that I want to make is, like, I'm using Cobalt Strike here. It's just what was easiest and most available to spin up. This is nothing Cobalt Strike specific. Like I mentioned before with the implementation of the automation, or like the BOF and the Python script that I'll release, you don't even, like, you can use any service control manager interaction for this. You don't need Cobalt Strike. You don't need like any proprietary solution to accomplish this. Use SSH, use another C2, there's a lot of ways to accomplish this in a similar fashion. So we have the SOCKS proxy, we have a regular domain user context. We run SCCM Hunter. For the sake of time, I've already done the information gathering for SCCM in the hypothetical target environment. So we see SCCM Hunter returns for us this nice view of like a primary site server, some hosts that could be related to like a site database. So we do just a quick port scan. Sorry, I kind of missed it there, but it was an in-map scan of the relevant port for MSSQL. So now we're relatively certain that one of those SCCM servers are associated with being like a site database for the SCCM site. We run this SCCM Hunter command that will query the appropriate LDAP-related information to construct this SQL statement, and we'll use this as part of the relay. So like when we coerce auth from a primary site server, then when the auth is successfully coerced and then targeting targeting a site database, this will be the SQL statement executed. It will hopefully add an administrative user to the site database. I know I'm kind of like glazing over some of the details. I'll elaborate on the unbinding of port 445 part, but this is all the SCCM Takeover 1 primitive, which if you're curious about the specific details or like how to abuse it, Chris, Dwayne, Garrett, all of the like SCCM crowd published a project called Misconfiguration Manager that gives an incredible amount of detail and reference to like how exploitation of this works. So we have the SQL statement, we've done some enumeration, we think we know where the site database server is. Now on our compromised host, we have elevated access because we do need elevated access to like disable these services, for example. So we run the BOF, we run check, everything's enabled, we can assume 445 is bound. Just for the sake of demonstration purposes, I just run a quick netstat command here. I use shell. If evasion is relevant, would definitely recommend not using shell, but just for the sake of simplicity, we run netstat, we kind of parse out what's bound to 445, and just like when we were stepping through the initial analysis, we see that the system process or a process of PID4 is bound to 445. Everything is kind of going as expected. We run stop, it disables the services, and now because ServNet is unbound, we can relatively safely make the assumption that 445 is no longer bound. We run another netstat just to make sure of that. Scroll through, 445 is no longer bound on the target host. And what this affords us the opportunity to do is, instead of having to do like, pause this for a second, instead of having to like load the WinDivert driver or load something into LSASS or reboot the host, now we can just jump straight into configuring that reverse port forward type functionality to where we can bind somewhere on the host, in this case just straight to 445, where in other cases like with Portbinder or other WinDivert related projects, we would probably have to bind elsewhere and construct or like create a redirection of traffic from like 445 to another port and then reverse port forward from there. This kind of cuts out one of those steps, and we can just bind straight to 445 because it's no longer bound to create our reverse port forward there. Oops, I think I restarted this. So we create our port forward, we bind to 445, and now hopefully when traffic comes from the target network, a lot of our relays, especially operating over C2, start with the coercion of traffic. And now we're bound on 445. When we coerce now SMB traffic, it comes to our host, hits where we've created that reverse port forward. It will tunnel out of the network over port 445. And then we fire up NTLM Relay X, and it looks like it's a huge statement here, but basically all we're doing is the way you would target any other MSSQL service for a NTLM relay like this. So it's just NTLM Relay X, give it a couple parameters, we're targeting MSSQL. The long, scary thing here is just that SQL statement that we generated earlier with SCCM Hunter. We fire that up. One thing I also like to note is that we start NTLM Relay X with proxy chains, because when we bind to that port, in this case directly to 445 now that we can just unbind that. We coerce traffic with something like printer bug or petit putam. That traffic comes back to us. Now it hits port 445. It tunnels out, very likely over our C2 channel. And then because we have NTLM Relay X listening, as well as running with proxy chains configured, when that coerced NTLM authentication reaches our attacker host through that reverse port forward, it hits NTLM Relay X, where it's waiting for the incoming connection, leverages SOCs to go back into the network and target the, in this case, SCCM site database. And then we actually coerce the traffic, in this case just using petit putam. That goes over SOCs, it hits the target host, and we see it go through the tunnels, the series of tunnels that we've created. It successfully reaches the site database server, and it's executed the SQL statement. We have now hopefully added our regular domain user as an administrator in the SCCM site database. So we use Garrett's SCCM Hunter again to connect to, we use the admin command, which is connecting to the admin service API, and we just say, hey, what's the admins here in the site database that we've now hopefully compromised, and we see that now the normal user one, the domain user context that we were operating in, is now added as an administrator in the site database, so that's good news for us. And then to just kind of like give like a relatively quick demonstration of like we're added to the site database. What do we do now to actually like compromise a privileged server in the environment? We get the device info for the primary site server, like the privileged machine that we want to compromise. We interact with it using SCCM Hunter. We try to deploy a script, and we see we need some approval credentials. This is relatively common with this type of SCCM-related abuse, but thankfully Garrett has already accounted for this in SCCM Hunter. All we need is any other domain user to elevate and be an approver of the script that we want to deploy. So now we just give it any other domain credentials as the approver for this. We will add that user also as an administrator in the site database. We can do that now because we are already an administrator. So we need the SID to do that. We get the SID of the other user, we add them as an admin, and then now we should have everything we need to go from just pretty much any domain user that has local admin somewhere in the environment to arbitrarily execute a script on the primary site server of this SCCM site. So we interact with the site server, we CD to C users public. All the script does is drop a file called we made it, and inside the file it'll tell us the user context. We do script to deploy that script. There's no output because it's just dropping a file to disk. We ls the contents of the folder. This is on the primary site server. We see we actually dropped a file on the primary site server, which is encouraging. If we cat the contents, it'll tell us what our user context is, and we've arbitrarily executed code on the primary site server in a system context. So now just another script is deployed to do cleanup of the file that we dropped, ls to make sure that worked, and the file is no longer there. So to kind of wrap up everything that we've covered and why I feel like this will hopefully be helpful for people doing NTLM relays over C2, for example, something that's very common for us, is just instead of potentially having to load a driver or do like things that could have OPSEC-related implications with LSAS, like loading custom authentication providers, hopefully you can just conduct a series of simple service control manager interactions using MyPOC or whatever your favorite service control manager related tool is, and ultimately end up with 445 unbound and do all of your SMB related NTLM relays using that now that 445 is unbound. And again, just wanted to note that remotely conducting these interactions with service control manager when you're disabling this port is probably beneficial to do leveraging RPC over TCP because you'll still be able to re-enable it remotely. The BOF and Python script will be released if you want a way to automate this relatively quickly. The code is written. We've been using it on assessments for the last 4 or 5 months, And I plan to release that here probably in the next 3 to 4 weeks. So that'll be on GitHub. And ultimately, my hope is that this provides a lower touch solution to have a way to control inbound 445 TCP traffic that will result in you more easily being able to conduct NTLM relays over C2. This whole, I again am biased. I've talked a lot about NTLM relays, but there's a slew of offensive related techniques where having control over inbound 445 traffic would be relevant. So NTLM relays is what I am preferential to, but hopefully this will help in more situations than just relays. And that's it.